So yeah, let's get started. I'm going to talk to you guys today about the verification of a distributed system. And the point of this talk is not to belabor formal methods and academic proofs, because people in industry don't use them. So we're going to talk about some real ways that you can do it. And I have to mention formal proofs just because they're a thing. And there is some interesting uses in industry that are happening right now. So let's get started. I'm Caitie McCaffrey. Like I said, I'm a distributed systems engineer. I've spent my career building mostly large-scale backends that power entertainment experiences and video games. So for Microsoft on the Xbox, so Halo series, Gears of War, HBO, and now I work at Twitter, where I was a tech lead of observability, and I've recently branched out into distributed build tools, which is super exciting. This is me on the internet. My DMs are open if you have questions or want to chat afterwards. Totally talk to me, because I like doing that. It's great to hear from everyone. Okay, so we're going to start this talk off with a quote from Leslie Lamport, because what distributed systems talk doesn't need a Leslie Lamport reference. So Leslie defined back in the day that a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. So back then, maybe that was fine. This is not okay today. If one computer goes down and totally breaks your whole system, then we have a really big problem, because your users are most likely being affected, and that impacts your bottom line. So the point of this talk today is sort of how do we increase our confidence that our system is doing the right thing, so that this one pesky computer going down, or multiple computers going down, or a data center going down doesn't affect our system, and it can keep running. I also want to take a quick aside to say we are all building distributed systems, even if you aren't building Google scale or Twitter scale or whatever, insert company scale. We're all building distributed systems, and we all have been for a while. Our clients talk to our services, which talks to a database. And this is even when we were back on one single database. And so this may be a small, simple system, but it's still distributed, because we're talking over a network, components can fail. And so all of these tools that we're going to go through today are applicable to any size system. Your system might be simple. It may be really large and complicated, like Twitter services. This is a trace created by Zipkin, which is our distributed tracing system at Twitter of all of our microservices. These have sometimes been referred to as Death Star architectures. So this is kind of crazy, and testing all of this is very important, because we want to keep Twitter up and running so you can use it. And then, sometimes we build these systems that are a little crazy, and you might sort of scratch your head and be like, what the hell have you built? But we still want to test these systems and make sure that they work okay too. Okay, so quick overview of where we're going to go today. We're going to talk about formal verification very briefly, and then just because it is sort of the gold standard of how we verify that our systems are correct. And then we'll spend the bulk of the time talking about how you can test your things in the wild. And while these don't give you a gold standard, like gold star of approvable that it's provably correct, it does give you a lot more confidence, and you can sort of mix and match which ones work for you based on time and budget and investment in tools and resources that you have. And then we'll briefly touch on some research that I think is really interesting that's giving us a new hope that maybe building and testing distributed systems is not so terrible. I'm going to go through a ton of information in this talk, and don't feel like you have to take notes or anything. I have a GitHub page where this talk is listed, and all of the references are also in there if you want to dive deeply into more. Don't worry about trying to read that. There's a bigger link at the end, and I'll tweet it out also if you want to look at it. Okay, so let's get into testing. When we do testing, and formally what we say is that we're trying to prove certain properties about our system. And we're trying to prove safety properties, and this is the idea that something bad will never happen in our system. And we're trying to also prove liveness properties, and this is the guarantee that something will eventually happen in our system, that our system can make progress. You can obviously simply build a system that has either one of these properties, exclusively, but it's generally not a useful system. Right? You can also think of safety properties as this idea of what is the system allowed to do. Basically, this could be a guarantee that all committed data, so all acknowledged rights, are persistent and correct and durably stored and will never be lost. Equivalently, you can also say a liveness property is this idea of what the system must eventually do. So this is an idea of when I receive a request, I will eventually respond to that request. So those are sort of very like formal terms of what we're doing when we're testing. Like I said, formal verification is this idea that sort of came from academia, and this is how we prove that systems are correct. This is really great because when we build like programming languages and things like that, we want to have an idea that they actually work, or a consensus algorithm. And this gives us this gold star, like our system is provably correct. We have math that has told us that the system is going to do what we think it's going to do, and that's really useful for certain things. Formal specifications generally use, so there are two sort of ones that people generally have heard of. There's TLA plus and then there's COC. We're going to go through a quick TLA plus example just in case you've never seen it and you're totally like, I've heard of this, and people talk about how terrible it is and boring, just because I think it's interesting to see. And this is a quote that, once again, Leslie Lamport invented TLA plus at Microsoft Research. And he writes in his book, Specifying Systems, which you can just read a PDF online. It's cool. It's a good idea to understand a system before building it. So this is the idea that we should like maybe design something before we start coding it. But he also goes on to say that it's a good idea to write a specification of your system before implementing it. So this is saying, like, let's define what properties our systems are going to have and that prove that these properties are going to hold and actually produce the outcomes that we think they're going to produce. So this is an example from Specifying Systems of TLA plus and the hour clock specification. So he basically writes a really simple specification of an hour clock. This is just the idea that it displays the hour from like 1 to 12. And so you'll write your proof and you'll define that, like, right, this one line is saying that like the hour can be 1 to the number 12, like those integer numbers, and then it defines how it updates. If it's 12, it becomes 1, otherwise it increments by 1, hour plus 1. And then you take this, this is like, it looks like code, right? And you take it and you run it, either use TLC, which is a model checker, or TLAPS, which is a proof assistant, and then you put your specification into one of those and it will tell you whether your system is correct or not, and then you have a verifiably provable system. So that's neat. Industry has actually used this. This is not just an academic thing. So in 2014, Amazon released a technical report on how they use TLA plus to verify 10 plus core pieces of their infrastructure, including S3. This is a super approachable paper, so if you're interested in maybe using this to verify key pieces of infrastructure, I highly recommend reading it. So we'll go through some of the highlights, but basically they declared at the end of this paper that formal methods have been a huge success. And they're now in their annual planning actually budgeting time into building systems so that they allocate engineering time to use TLA plus and write specifications for their crucial pieces of infrastructure like S3. When they did this, they found 2 very serious bugs that they say they couldn't have found in any other manner of testing. And then it also allowed them to increase confidence to make all these sort of like very complicated perf optimizations that were changing the underlying implementation and the algorithm quite a bit. And they felt that they wouldn't have had this confidence to make these optimizations in these core pieces of storage, because that's kind of risky, without having a formally correct proof. So this is sort of cool, like if you are building something that other people are going to use, heavily rely on, like a storage system or a database, or you're offering something as a service, like maybe this is something you want to invest in, especially if you have strong consistency guarantees around it. They do call out also in this paper that and this is typically one of the biggest criticisms of TLA plus and formal methods, is that you write this logic, or this like your formal specification code, and that's not code that generally runs your system. And so you could have a totally correct specification of your system, and your code that you write is still wrong. And that's like a challenge, right? It's worth noting that COC, which I didn't have time to go into, actually can generate Haskell or Objective Camel from the specification, and that is runnable for a subset. I don't believe it does the whole language. I believe it only does a subset of the language, because you have to be able to prove properties that like it terminates, and you like can't do that with most languages. So that's like something that sort of helps bridge the gap, but obviously we still aren't all the way there. Even if you have a formal specification, you probably still need to test the code that you wrote. So let's talk about how we're going to test the code, how us practitioners are going to do this in the wild. And so while we may not get this idea of a formally correct or provably correct system, we get this idea of it seems pretty legit. So I'm going to put it in production. Okay, this is super basic. I don't want to belabor unit tests, but like write them, please. So typically this is like the idea that it's implemented by the developer who is writing the code. It can be ran locally with CI or no environment needed. It's just your CPU. And this is to verify basic functionality in error cases. This increases your confidence that your code's actually doing the right thing. Typically, I like test cases for it's increasing my confidence that, like, 6 months down the line, my code's still doing the same thing when someone is, like, done a big refactor or changed an implementation. And now I would like to break for a brief rant of Festo, because if you're going to the programming languages track or anything, or you used a typed programming languages, types are not testing. Typed languages are great. I actually prefer to use them, so I want to totally like talk about my bias, because this is a perspective. But like when you're writing in a typed language, it only gives you so much. It can only prove as much as your type system is, as expressive as your type system is. So this is like a brief example in Scala. I define a method add, and then like I make a dumb typo, and I'm actually multiplying the values on return. So like obviously the type system has not made the system correct. This is going to return the wrong thing. A unit test would find this. And I sort of break here because I think it's sort of there's a lot of debate in the programming community, but we don't have expressive enough programming languages in the ones that we're typically using in industry to like rely on this. There's actually research going on that may make this better, but we're not there yet. I also sort of want to call out that this is a thing that happens a lot. There was a story of a younger developer that I was working with at one point, who he was very enamored with type systems and the mathematical proofs behind them and type theory, and that's great. But he believed that you didn't have to write test cases. And if you're on my team, you're going to write test cases. So, like, caveat if you ever want to work with me. So I wrote in a code review that, like, hey, you need to add some test cases to this. And then I, like, went through and did a thorough code review. And I actually found a bug, which was his recursion algorithm would never exit. It would actually recurse forever and could blow up your stack. And so if you deploy this into production, it's going to cause a bad time. And a simple unit test case would catch this, right? So, and then I, very nicely wrote back, because I wanted to use this as a teaching moment, that, hey, I think there's an infinite recursion bug here. Could you please add a test case specifically for this? And he did. And then we all moved on and our lives were better, right? I also want to point out that like TCP doesn't really care about your type system, so when you start going over the network, like all bets are off, and your type system isn't going to help you here yet, right? Once again, programming language research people who may be in the audience, please solve this problem for me, but like TCP doesn't care. So this sort of brings me to my next topic of you need integration tests. And I know there's a lot of different testing methodology in industry, but I sort of define integration tests. If you're going to stand up some kind of environment, you're going to write these tests so that you're exercising sort of the network boundaries between your systems. So this is talking to your database or testing your network protocol, testing versions of your network protocol, also important. There's this fun sort of story that I had when we were shipping Halo 4 that we caught a fairly large bug that would have really hammered our system at launch because we had proper integration testing. So I worked on the statistics service of Halo 4. You uploaded your stats at the end of a game, and we processed them. We noticed during integration testing that the game was consistently uploading the stat blob 3 times. And this thing is big, and it's expensive to process, so like doing 3 times the load that we had projected would have been a really bad time in production. And so I'm going back and forth with the network developer or the game dev who's responsible for this feature on his side, and I had written the API on our side, and I'm like, look at our logs. We're returning an HTTP 200. Like, why are you thinking we failed and keep sending it to us 3 times and still think that you failed to upload stats? And he's like, I don't know. Like, you guys must be sending us something wrong. And we had this nice little banter back and forth. And eventually what we found out is that because of legacy code, what the game code was actually looking for was the words done in all caps in the payload exclamation point to mark a thing as a success. So integration tests are really useful because it's testing the breakdown between your interfaces, right? And once again, like very smart developers do very different things, and we all have to deal with legacy code, so we should exercise these boundaries and prove that they're correct before we just sort of throw code out there to our users to test. Also, to support unit integration tests, there's this really lovely paper that's probably one of my favorite from 2014, called Simple Testing Can Prevent Most Critical Failures. And what the authors did is they studied 198 randomly sampled real-world failures reported on open source software. So this included things like Cassandra, HBase, HDFS, MapReduce, and Redis. And then they have a ton of information in this paper. But I'm going to go through some of the key highlights that I think are really interesting, but also like go read this paper too. So one of the key findings that I think that was super interesting because it debunks a popular myth that you need like a whole giant staging environment that looks just like production to reproduce some of these like nasty production level bugs, is that out of 98% of the failures that they analyzed, 3 nodes or less can reproduce this. You can stand up 3 nodes on your laptop and run it, right? So like we can stand up 3 nodes in a dev environment. That's super cost effective. It's super cheap. So there's really almost no reason we shouldn't be doing this level of testing. It's really effective in finding failures in our systems. And when I say catastrophic failures, what they're talking about is like data loss, system crashes from these core systems that are actually supposed to be very stable and store our data and be very reliable. So this is like do integration tests, right? Another thing is testing error handling code could have presented 58% of catastrophic failures. So this is, once again, we didn't write unit tests that tested anything besides the golden path, or we didn't write unit tests at all. And so what this says to me, and as a practitioner, and one thing that I took to heart, is use a code coverage tool. I know code coverage tools are super, like it doesn't tell you if you have 100% coverage that your code is correct, but it gives you an idea where you have a gap. And if there's like all these big, like, oh, we didn't test the error handling cases, like 58% of catastrophic failures were caused by error handling, right? Yeah. So do this. It's super easy. Like, I know writing test cases isn't the most fun thing in the world, but like, we get paid for this. Also, what I think is interesting here is that, like, and we've all done this, right? Like in Gears of War, we were like investigating a bug after launch, and we're going through the code base, and we find this, like, if do this, else if do this, else error. Please fix K thanks bye in a comment, and there was like no code there. So that actually wasn't the bug, but like I think we all have these in our code bases. So just actually handling them will help us a lot. Finally, the last point from this paper that I'm going to leave you with today is that 35% of catastrophic failures were caused by very, very basic things, like error handling code is simply empty or only contained a log statement. They actually found in the paper that most of the catastrophic errors were logged, so that's at least good, right? You have information to go fix them, but they just weren't handled. Error handlers aborts the cluster on an overly general exception. So this is like, oh, catch exception, and then like, tear down the cluster, which is bad. So maybe like do a little more thought about how your systems are supposed to fail. Or this idea of like error handler code contains comment lines like fix me or to do. This is laziness, right? And this is causing catastrophic failures in our system. And like, so just like we talk about how terrible and hard distributed systems are to build, we can fix a lot of those problems by just doing unit and integration tests. And this paper sort of showed us that. So I really like this paper. I'm actually going to be talking about it at QCon, or at New York's Papers We Love in June. If you're there, come say hi. Okay. So let's move on to something that maybe you haven't heard about, and is not just me ranting about write test cases. This is property-based testing. So this is sort of inspired by like model checkers, which are actually like a formal method of verifying where you go and actually exercise the entire state space of input into your system on that formal specification. So what property-based testing does is this is made more industry friendly, and they're going to execute. You're going to write properties about your system that you want them to hold, and then it's going to execute randomly over that state space. So while it doesn't prove that your system's correct, it is exercising more of the state space than just a single unit test case can. There are a ton of tools to do this. QuickCheck it was invented by John Hughes, and that was sort of the first one, and there's a version in Haskell and Erlang that you can use. And so what you do here is you define the specification instead of a test case, or you can write both if you really want. You use a tool that generates many inputs to test the scope in the specification. And what's super nice is that if they all pass, then you get a green thumbs up. And if one fails, it'll actually tell you like the specific use case that caused the failure. So then that gives you a lot of information to go and start debugging this, right? It's not just like, oh, like something failed in the wild and now I have to go scrub through like, miles of logs to figure out what happened across my system. That's annoying. This is really nice. And then one other quick note from that previous paper about testing and catastrophic failures is that they sort of found that basically like 3 inputs or less could reproduce most catastrophic failures, and the order was deterministic. So if you can define your properties broad enough, you may catch them with a tool like this. So QuickCheck's the original one. I've used ScalaCheck. That's written in Scala and Java and on the JVM. And then if you want to use it, like all these languages down here also have QuickCheck ports. And I linked to this from references, because if you can't read all that. But basically, there's one of these for almost any language that we're using in production today, which is cool. It's also worth noting that QuickCheck is really great because it's been used by successfully used by companies like Basho, which has Riak, which is a NoSQL eventually consistent data store, and they have a great talk on how to sort of model eventual consistency properties. That's in my reference section. Using QuickCheck. They've used it to find QuickCheck to find bugs in Volvo cars, and most recently there was a talk and a paper published about how they use it to find bugs in Dropbox. And so these are going to discover some of your more gnarly bugs because it's going to exercise over a larger set of inputs than you just have to like think about. Just a super quick example so you can basically see, like, this is not, I'm not asking you to write a crazy specification. This is the ScalaCheck one, because that's what I've used. So this top one is basically saying, I'm going to define a type small integers, and then this is a basic level property. You can, like, combine properties together to make more complicated statements. But it's basically going to say that, like, the number should always be between 0 and 100. And so anytime I sort of see this, then, you know, that property will hold. This second one is how to reverse a linked list, or reverse a list. And so it says, you know, the reverse of a list should be equal to the list. And then, like, what ScalaCheck will do is go and generate a bunch of inputs to this and ensure that holds. So you didn't have, like, an off by one error or, like, you know, whatever, like some bug in your system, and it'll return you a counterexample. So this is pretty easy to do in you know, I think for the basic stuff is very similar to writing unit test cases on the investment time, and you can obviously do way more with this. So I like property-based testing. I'm encouraging a lot of my teams to use it more because I think it finds a lot of bugs, and it's sort of low investment for high reward. Finally, I want to move to fault injection, which is another way that we can test distributed systems. I think this is particularly useful for distributed systems because we're basically forcing our systems to fail, and then we're observing what happens. I fully believe that if you do not force a system to fail, all the theory and, like, proofs in the world, like, besides formal specifications, are basically not going to give you shouldn't have any confidence that it's going to operate correctly in failure modes. So you should stand it up and force it to fail and see what actually happens and prove out your design. One example of a fault injection system that you're probably familiar with is Netflix Simian Army. I'm not going to spend a ton of time on this, but I like to, like, show it as, like, this fits into that classification of tests. So this is, like, they have Chaos Monkey, which kills random instances, Latency Monkey, which introduces network lag in between packets, and then they have Chaos Gorilla, which takes out an entire availability zone to make sure that they're multi-DC tolerant and things like that. Obviously, this is a ton of investment, and we don't have to go this far with fault injection testing. You don't have to build something of this scale to get benefits of it. Another popular fault injection test is Jepsen. So this is a tool that's open source that was written by Kyle Kingsbury. And what it goes is it simulates network partitions in the system under test. And then after the test operations and results are analyzed, it'll basically say, like, did your claimed consistency guarantees hold? Were they upheld? He's used this to test a bunch of different systems, including, like, MongoDB, Elasticsearch, Kafka. There's a whole list on his website if you want to go read them. And basically what Kyle sort of showed us as he started doing this a few years back is that the distributed systems we rely on are maybe not as reliable as we think they are. And this isn't because people are bad people or bad developers. It's just because distributed systems are hard, and predicting all of the failure cases and dealing with partial failure and asynchrony is hard. And so what's really great about this project, I think, is that he publishes these results. He files bugs on GitHub and open source projects. And then a lot of these things have been, like, fixed, right? And systems are getting better. The goal is not to, like, make fun of people by finding bugs. The goal is to, like, make the systems better that we use. Although, like, this image is hilarious, and these were drawn by Kyle, and he let me use them. Also, you can, like, now pay Kyle to Jepsen test your system. So if you're building, like, a database or something that's like a piece of infrastructure, maybe do that. I want to pause really briefly to be like, passing, none of these tests I've shown you, while they will increase your confidence that your system is doing the right thing, passing them does not ensure that there are no bugs in your system. There still could be bugs, but we probably have the more of these we use and the more these tools that we use, the more confidence we have that our system is doing the right thing. Another final method of fault injection tests is this idea of game days. So this was developed by Jesse Robbins at Amazon in the 2000s. And he actually had the title there of the master of disaster, because basically what he would do is he would just go break production. And he would do this in a responsible way, where he would tell engineers that there's going to be a major outage in 3 to 4 months, get your systems ready. And they wouldn't know exactly what the major outage could be. It could be, we lost an entire data center. I guess one time they mimicked that there was a fire in the data center. Or you could lose a rack or a series of racks and reduce your capacity significantly. And so the idea here is that, A, we're telling developers, like, your systems are going to fail, plan for it, and make them more reliable. And then the other idea here is that they're testing their people processes in addition to their systems. So the system failed, and now we have our DevOps people and our on-call people trying to fix it. And how do we ensure that it's fixed, right? Like, are those processes also good? Where is the breakdown in communication there? So you're testing your people and your processes in addition to your software. So this has been used in a bunch of different things. It also helps you if you have a ton of data centers or POPs or instances installed around the world. If you become more global, figuring out where you have these weird hidden dependencies. I think they found a bug where basically the data center they took out contained it was the only instance of their paging system. So like no one got alerts that the data center was down. And that's kind of bad. But like this is how you find these things that are, maybe more operational, maybe more config-driven error. Those are still very difficult things to test, right? So if you want to run a game day at your company, how do you do this? And it may not be like as involved as like an Amazon one, right? You're going to notify your engineers that a failure's coming. Like you probably shouldn't just like pull the plug one day and be like, surprise. You're going to induce a failure then at some future period of time. You will monitor these systems that are under test. Typically, there will also be an observing only team. So they're sitting there and their job is to monitor the recovery process. So this is how you find the bugs in the people processes and where the breakdowns are. You don't want the devs who are sort of like, oh my gosh, like we just lost an entire rack, the system's on fire, and trying to fix that to also be trying to evaluate like the processes. This is the idea of having an objective observer. And then when you're done with that, you need to sit down and go through the list of like, here's where everything failed. You want to prioritize those bugs and get buy-in across the teams. Because typically where they found failures in this, especially in people processes, is across team boundaries, right? Because that's always where the breakdown in communication is. Okay. Just to sort of point out like how simple this can be and like how critical of bugs it can find, Stripe wrote a blog post about how they ran a game day. And all they did is they basically ran kill 9 on their primary Redis node. And then it went down, and like the other two like started handling requests, and that was fine. But then it came back up, and it had no data, and it decided it was still leader, and it propagated the fact that there was no data in the cluster to everyone in the cluster, and they lost all of the data in the cluster. So that's bad. Luckily, they had done a backup because they knew they were doing controlled failure. And so, right, there's this tweet that Kelly Summers made at the same time once this blog post was published, because like, I don't know if you guys were on Twitter when this happened, but it was really entertaining to watch Twitter while this was happening. But basically this idea of like, in industry, we need to be better about this. Just running kill 9, just like literally like shooting a node in the head in a test environment or like in production can like lead to really disastrous results. And it's worth noting that like what they did is like the Redis author came back and said after this outage that he had not expected the configuration that they were using, and that's why this failure happened. So this sort of harkens back to, especially in this open source world, if we're going to pick up a dependency and use it, then it's sort of on us to vet that dependency, right? Especially if it's a critical piece of infrastructure. Because, especially with like these crazy config databases and things like that, and like distributed queues and all that kind of stuff, if you're gonna stray from the normal, like you may have a problem because that path may not have been totally thought out, or you may be doing something that the authors never thought you were gonna do and therefore was not well tested. Okay. We're going to take another quick little Rantifesto break because I have some thoughts about testing in production. That was ran in production. That test case didn't need to be ran in production to prove that failure happened. So I think there's a lot of value in testing with production data. I'm a big believer of that. I tend to use, in a lot of my systems, have ways to fork in production data to test things and test in staging. And we're going to talk about some actual testing in production code. But you're impacting your users at this point. And that's problematic because your users are having a bad time when your system fails in production. So it's this risk versus reward thing. If it's not a super critical system, maybe it's fine to test in production. But if this is like a critical backbone piece of your infrastructure or like core component of your service, the risk is pretty high to just sort of like, send some untested code out there and be like, it's fine, or not, and then roll back. So I just sort of wanted to say that. I think, there's a lot of like hype around testing in production, but that doesn't mean like testing in production should be the final step. We should have a lot of confidence and have implemented some of these other things in staging environments or in unit tests and integration tests to prove that we think our system works. I also want to say that like monitoring is not testing. People say this to me a lot because I ran the observability team at Twitter, and I'm like, monitoring is not testing. Monitoring is super critical to your system and understanding what's happening in your system and recovering from failure in your system, but it's not testing. All it's going to do is like tell you that if you have a graph that happens to show a failure, that like maybe you'll see the failure if you happen to be watching the graph, or maybe you'll get a page, right? But this is a reactive approach. This is not verifying that your system's correct. It's just sort of telling you what's happening. So have monitoring, but like do more things than just monitoring to test your system. Finally, another way to verify in production, I call it verification, right? Because like at this point it's already impacting your users, so is it really verification? Is that, and I think this is actually a really good process. I'm not like trying to say don't canary, but do other things first. This is sometimes called like red-green testing or whatever, but the idea here is that you gradually introduce new code into production, and this greatly reduces the risk of doing deploys and is actually super powerful from like an operations perspective. The canaries have a lot of limitations. So canaries are only going to tell you that the golden path typically is working, right? That you haven't like broken user functionality that they're using all the time. Because canaries can only tell you that they perform as well as the old version at this exact moment in time. And so unless at this moment in time there is a network partition happening, or a data center is down, or some other failure is happening, you don't actually know if like the canary is just as good as the old version. It verifies the golden path. And that's all it gives you. And so I think super powerful tool, use it, but understand the limitations. People were like joking, they're like, why isn't there a canary bird? This is a Canary Island butterfly for people who are using my slides. So I tried. Okay, so we just went through a lot of things about verification in the wild. Like obviously I'm very realistic about the fact that there are deadlines and that we only have so many resources, and so like maybe we can't all build a Simian army or don't have the time to like Jepsen test every system we build. But we do have the time to write unit integration tests. That should be like base level engineering effort. And like that paper that we went through shows that they're incredibly, incredibly valuable. Property-based testing, I think, is also fairly low investment and high reward. So I would highly encourage, if you haven't used it, try it out on some of your projects. Fault injection also can be very low investment and high reward, as we saw with the kill 9 nodes. Maybe do it in staging first. And then right, canaries are a nice process to sort of like reduce the risk of deploys and prove that this new code hasn't totally broken user functionality as we roll it out. And realistically, I like canaries for testing that I didn't screw up my configuration somehow. That's at the level of what I'm actually testing at that point. Okay. So let's take a quick moment to go through some research. I'm not going to go through all of these today. These are just things that I think are particularly interesting that are currently happening within the last year or so. And I have links to all of them in the references section if you want to explore further. But we're going to go through one that I think is really cool and also ties into industry because it's called lineage-driven fault injection. So this is a paper by Peter Alvaro from UC Berkeley. He's now a professor at UC Santa Cruz. And so the idea behind this paper is, and this tool that he builds to go along with it called Molly, is that a lineage-driven fault injector is going to explore the state, like try and explore the state space of like all inputs and failures that could happen, but it's only going to do that for the ones that actually matter. So it starts with a successful result of like, I stored something and it's durably stored in my database, right? And then it's going to go look at like all the graph, the call graph to figure out what happened and start like axing like requests or things that happened along that path and start injecting failures only along that path. So then we only test the things that actually could affect the system. And this gives us provably correct. So that's nice, right? And you can run through the state space of failures in a smaller amount of time than some model checkers can. So this is an example from the paper. He uses it to replicate a bug that had been in Kafka a few years back that I think Jepsen actually found. But there was an issue where like if a network partition happened, this node on the far replica A becomes the primary, and it's also the sole member of the cluster because B and C can't talk to the zookeeper that is determining membership. A then acknowledged a write from the client and said, like, I've durably persisted it, but then it crashed. And so that write is lost because it wasn't able to replicate it to anyone else in the cluster. This paper didn't find this bug, but it is proving like this is how we would find it. And this bug is fixed now, right? Like this is like an old bug. But it was an important one to sort of show because like this is a very, like what's happening here is very complex. There's multiple systems involved and multiple sort of like protocols that are doing like reliable broadcast. So this is kind of cool because then like when you run something through Molly, it'll give you the exact use case where something failed, and this is much easier to understand. Like we can all look at this and be like, oh, like A shouldn't have acknowledged that right? Like that's clearly the problem. But it's much more easy to reason about the failure, I think, in this model. I think Molly and lineage-driven fault injection is super cool because Peter actually worked with Netflix and implemented this in their sort of fault injection model. So Peter and Colton Andrus from Netflix partnered to like make a prototype of this. And there's a lot of interesting things that happen when you try to take like a research project and then like put it into production. And there's a really amazing talk that's linked in the references that they give about it, and there's an article as well. But some of the key findings were like, this is like the Netflix Death Star microservices diagram that I borrowed from Adrian. And so like maybe we don't have a whole graph of like what's happening in the system and all the systems that are talking to each other because like that's not discovered a priori, that's defined via code. And so they use distributed tracing, and they have a tool already called FIT, which is their fault injection system to inject failures, and so they know points where they can inject failures into the system. So they use that to construct the call graph. So they're doing it sort of like live, right? And they use the metric system to determine if the call was a success or a failure, because they have all these like, an HTTP 200 wasn't enough because you have all these sort of like weird, certain clients, behave badly if you send them a 500 back, and they have to support a range of clients, and like whatever. The world of like the internet is terrible, so fine, we do it, and we use metric systems to determine if the call is a success. And then like Molly would sort of like process this call graph and stuff like that, and then determine where FIT should inject a failure, and then they could figure out like had it happened. And there's a couple other interesting things that they had to go, problems they had to go solve. And so I highly recommend like reading the talk, but it's really cool because they ran and they found some bugs, and that's a good use of like how do we start thinking about integrating some of these things into production environments. Okay, so in conclusion, use formal verifications to test your critical components. If you have something that is super mission critical that maybe you are selling and making money off of, it's not a bad idea to write a formal specification and invest in that software. I think unit tests and integration tests should be like, they find a multitude of errors, and they should be bare minimum for any software that you're writing. And then, we can increase our confidence using property testing and fault injection in our systems. And I think these are highly underutilized, and this last bullet point is sort of where we can see a lot of gains for fairly minimal investment. And then if you're a giant company, you can go and build these sort of like really large tools. And finally, I'd like to end with a quote from my friend Camille: enjoy the ride, have fun, and test your freaking code. Thank you to all of these lovely people who helped me with this talk and the article.